Hi, today we're going to be talking about reaction mechanisms, what they are, and how we can use them to determine the rate law for a reaction. So let's think back to the collision theory of reactions, which says that the molecules must collide at the right angle and with the right speed for a reaction to occur. So here I have a reaction in which oxygen, two hydrogen ions, and two electrons all combine to give one molecule of hydrogen peroxide. Let's imagine the collision that would have to take place in order for that to work. For simplicity in this cartoon, I've left out the two electrons. I just have the oxygen and the hydrogen ions moving around. As you can see, it's not terribly probable that even two of the molecules will collide, so getting three of them to collide is almost impossible. In general, what we're going to see happening is that we'll have only two collide at a time, and so we will end up with a multi-step process. A balanced chemical equation represents a net process. Do you remember the net ionic equations that you did earlier in Gen Chem? We will be using a similar process to create balanced equations from different steps of the reaction. The difference is that in a reaction mechanism, things have to happen in a particular order, and so a reaction mechanism will show this. Basically, what we're going to be doing is breaking everything down into steps, each of which involves only one or two reactants. We call each of these steps an elementary process. As I said before, each elementary process has only one or two reactants. If it has two reactants, what we call a bimolecular process, what is happening is that the two reactants are colliding to form new molecules. If there's only one reactant, what we call a unimolecular process, the single reactant is going to break apart. One thing you may be asked to do is to determine whether a balanced equation represents an elementary process. To do this, remember that elementary processes only have one or two reactant molecules. So let's look at a few examples. The first one has butane, C4H10, reacting with oxygen, O2, to form carbon dioxide and water. This is a simple combustion reaction that has two reactants, butane and oxygen. But it has more than two reactant molecules. We have two butanes and 13 oxygen, so 15 molecules total. This is not an elementary process. In the second equation, we have dinitrogen dioxide, N2O2, reacting with hydrogen gas. Again, we have two reactants, but do we have two reactant molecules? This time we do. We have only one molecule of N2O2 and one molecule of hydrogen, so that's two molecules total. So now let's go back and look at the balanced equation I showed you earlier. Is this an elementary process? Well, we have five total things reacting. One oxygen, two hydrogen ions, and two electrons. So this is not an elementary process. The way this reaction happens is through a series of elementary processes. Here they are. First, oxygen takes an extra electron to form superoxide. Second, superoxide reacts with the hydrogen ion to form the hydroperoxyl radical. Third, the hydroperoxyl radical picks up an extra electron to form the hydroperoxyl anion. And finally, the hydroperoxyl anion picks up a hydrogen ion to form hydrogen peroxide. So why do we even care about reaction mechanisms? First of all, we can use reaction mechanisms to identify catalysts and intermediates. And secondly, we can use them to predict the reaction order of the kinetic rate law. Remember that I told you that we can only determine the rate law experimentally, and that's true, but we can usually come up with a couple of possible reaction mechanisms for a given reaction, and we can use those reaction mechanisms to determine the possible rate laws for that reaction. So let's talk first about catalysts and intermediates. What are those? I'll start with catalysts because those are the ones you're most likely to have heard of. A catalyst is a substance that changes the rate of a chemical reaction without being used up. Another way of saying this is that a catalyst gets used in a reaction as a reactant, but it's also produced as a product. So you end with the same amount that you started with. An intermediate is a substance that appears during a reaction. That's the product of an elementary process, in other words. And it also gets used up before the reaction finishes, so there will be none left at the end. So let's talk about using reaction mechanisms, the set of elementary processes that make up a reaction, to find catalysts and intermediates in a reaction mechanism. The first step is to add elementary processes to get an overall reaction. We do this just like we used to do the net ionic reactions. The second step is to cancel out anything that appears on both sides to get the net reaction. Again, just like what you did with net ionic reaction. Now, anything that cancels out will either be a catalyst or an intermediate. So now we have to determine which is which. A catalyst is something that you start with and end with. Remember, you always end with the same amount you started with. So you see catalysts in the products of the last step. And then an intermediate is something that appears in the middle. It might be a product in the first step, but it can't be a reactant. It can't be something you started with. So let's look at an example reaction mechanism here. Here we have two elementary processes, and the first thing we have to do is add them together. So how we're going to do that is take everything that appears on the reactant side of each of our elementary processes, and we're going to put them all together. Next, we're going to take everything that appears on the product side of each of our elementary processes, and we're going to put all of those together. Step 2 is to cancel anything that appears on both sides of the equation. So we have NO2, one of those cancels out, and we have an NO3 on each side as well. What we're left with is what we call the net reaction. But now we want to identify catalysts and intermediates. Remember, those are going to be the things we canceled out, which in this case were an NO2 and an NO3. So catalysts are anything we find in both the reactant side of the first step and the product side of the last step. Do we have anything like that? We do see NO2 in the reactants in the first step, as well as the products of the last step. So NO2 in this case is a catalyst. Again, intermediates appear sometime after the reactants of the first step and are used up before the end of the reaction. NO3 appears in the products of the first step and the reactants of the second step. It does not appear in the products of the final elementary process or in the final balanced equation, so it's disappeared. NO3 is an intermediate. Now let's use a reaction mechanism to figure out a rate law. To do that, you need to understand what we call a rate determining step, and that's easiest to understand if we use a metaphor. What determines how fast you can drive on a highway? If I asked you this in class, you'd probably all give me a range of answers like, how good is your car? What's the speed limit? Do you actually care to stay under the speed limit? But in reality, the truth of the matter is, you can only really drive as fast as the slowest car in your lane. And if all the lanes are filled with slow cars, you can't go 90 miles an hour. Reactions are the same way. Some of the steps go slowly, while others go more quickly. And the rate at which a reaction can occur is limited by that slowest step. We call that slowest step the rate determining step. It's like the pokey car that you get stuck behind that keeps you from going faster. The rate law for the rate determining step determines the rate law for the reaction. So remember that elementary processes involve either one or two reactants. If you have a unimolecular process, the rate law is going to be proportional to the concentration of that one molecule. In other words, it's going to look like this. The rate of the reaction will be the rate constant times the reactant concentration. Now, if you have a bimolecular process, the rate law is going to be proportional to the concentrations of both reactants, and it will look like this. The rate of the reaction equals the rate constant times the first reactant's concentration times the second reactant's concentration. Here's an example of an elementary process. What sort of elementary process is this? Well, we only have one reactant, ozone. So this is a unimolecular process. And because it's a unimolecular process, we're going to use this generic rate law. But let's substitute in our actual reactant, and we'll get that the rate of the reaction is the kinetic rate constant times the concentration of ozone. Here's another example of an elementary process. What sort of elementary process do we have here? We've got methyl bromide and hydroxide for our reactants, and with two reactants, we must have a bimolecular process. So now we're going to use this generic rate law. Now let's go ahead and substitute in our actual reactants, and we get this rate law that includes concentrations of both methyl bromide, and hydroxide. So now that we understand the connection between elementary processes and rate laws for those processes, let's use a reaction mechanism to determine the rate law of a reaction. This is a four-step process. First, locate the rate determining step. How will you know which it is? At this level of chemistry, the problem will tell you how fast the steps go. You're going to pick the slowest one. Second, identify what your reactants are in the rate determining step. Third, based on the number of reactants in step 2, pick the appropriate generic rate law and substitute in the actual reactant concentrations. Finally, if any of the reactants in the rate law you created in step 3 are not reactants in the overall net equation, you need to rewrite those reactant concentrations in terms of the concentration of a reactant. Now, I know that sounds complicated, and I hope it will make more sense when we actually do a problem. So let's start with a problem, and I've picked the easiest sort, the sort where the first elementary process is a slow one. Step 1 of our workflow has us identifying the rate determining step by looking for the slowest one, which in this case is clearly the first one. Now, step 2 tells us to identify the species that are reacting in that rate determining step. And what's going on there is that one NO2 molecule is reacting with another NO2 molecule. So now let's write the rate law using the concentrations of our actual reactants. This is a bimolecular process, so we're using this generic rate law. And now let's plug in our 2 reactant concentrations to give us this. Now, normally we don't write the concentrations this way. We can simplify it, and you can see that this reaction is second order with respect to NO2. NO2 is a reactant in the net reaction, and so we don't need to do step 4. Now let's do a harder problem, one where the first step is not the rate determining step. So here we have a 3-step reaction. So first we have to locate the slowest step, and here that is step number 2, which says slow. What species do we have in our rate determining step? NO2 and hydrogen. So let's write the rate law. Again, this is a bimolecular process, so we'll use this generic rate law. Plug in the concentrations of the reactants of the rate determining step to get this. And now we're on to step 4. Let's write the net equation for this reaction. If you add up everything on the reactant side, this is what you get. And then you add up everything on the product side, and you get this. We can cancel out the N2O2, that's an intermediate. We can cancel out the N2O, that's also an intermediate. And here is what we're left with. Now, if you look at the reactants, you see that N2O2 is not there. We determined earlier it was an intermediate. We have to write the rate law in terms of reactant concentrations. Why? Because we can measure them. Intermediates like N2O2 often only exist for teeny tiny fractions of a second, so we can't figure out rates based on their concentration. So here's both our net balanced equation and our rate law. And what we want to do is rewrite this rate law so it only uses the reactants in the net equation. The key to doing that is in the first step. All of the N2O2 here is created from NO reacting with itself. So the concentration of N2O2 is going to be some constant times the concentration of NO squared. Plug that into our rate law, and we get this. Right now, we have 2 constants, the purple K from our original rate law and the green K that we get from the relationship between the NO concentration and the N2O2 concentration. What's one constant times another constant? It's a third constant, which I have represented here with a red K. This is what our actual experimental rate law will look like. A rate constant times the concentration of NO squared times the concentration of H2. Reaction mechanisms are a useful tool for understanding how reactions occur and why we have the rate laws that we do. I hope this was helpful, and I'll see you again soon.